Assalamualaikum and hi again everyone. So in this lecture series, we are going to move on to a new chapter finally, which is chapter 5 on the topic of equilibrium of a rigid body. So if you manage to successfully practice throughout tutorial 1, 2, 3A and 3B, then the transition to this new chapter would be very easy peasy for you. Seriously, no kidding. Okay, so get your fundamental right, then only come back to this chapter. So as usual, for the convenience of the learning process, I'm going to divide this lecture into 3 smaller segments, which covers the rigid body equilibrium in 2D plane, 2 and 3 force members, and finally the application of equilibrium in a 3D system. If you can recall from the first lecture, we actually covered on defining the rigid body. As the name goes, rigid body is an idealization used in engineering mechanics, which simply assumes that the body does not easily deform when it is being subjected to external loads. Okay. In the state of equilibrium, we simply assume that all forces acting on the rigid body would sum up to zero, either it is in X, Y or Z direction. Okay, so since last week we also covered moment juga kan, accordingly in equilibrium state we also consider that all moment acting in the X, Y, Z direction would total up to zero as well. In the previous lecture, we only consider external forces which were subjected to the body. The forces are represented with direction of an arrow. So, in actual engineering application, certain rigid body connection would also create a kind of friction force. Okay, for example, if I were to take this Tupperware or this container and put it on the table, okay, can you see it? Okay, I cannot move it further downward even if I force it with my hand. Okay, so definitely there is an external force acting downward which is subjected by my hand. At the same time, there is a reaction force from the table upward towards the container which resists the downward movement. So that kind of reaction force is what we want to study in this lecture. Okay, that force is known as the support reaction. The support reaction happens when the body is in contact to another surface or another support joints. The main question that we need to address is, how do we define the support forces? Ke atas ke bawah ke kiri ke kanan ke? The principle is very simple. Basically, the first one is, if the support and the contact does not allow translational movement in that particular direction, then the reaction force is developed at that particular point, which is opposite to the restricted motion. Take example of this beam which is in contact with a roller joint. The beam can roll to the left and to the right because of the roller, so there is no reaction in the X direction, but it cannot move downward. Okay, so there is a support reaction in the y-axis which resists the downward motion. So in this case, there is only one support reaction acting on the beam. The second principle is, if the support or the contact does not allow rotation in that direction, then reaction moment is developed at that point. Okay, so you see, kalau tak allow rotation, then ada moment. Kalau tak allow translational motion, then ada force. Okay, take example of this fixed support. This kind of support does not allow translation either in X or Y direction because it's fixed. So, as we described previously, there is a reaction force acting in the X and Y direction. At the same time, the rotation motion is not permitted as well. So, there is a reaction moment at that particular point. How about the direction? Clockwise ke counterclockwise? Okay, at this point, you have to put in mind, this is just an initial assumption. So, the direction is not crucial. What's important is that when you have developed the correct free body diagram, then only you can perform calculation, apply the equilibrium condition, and the final value that you get from your calculation would be the determinant factor, which shows if the direction that you assume is correct or is it in the opposite direction. As simple as that. Okay, here is a list of different types of connection and its corresponding support reaction. Okay, different type of joints or different type of support type will correspond to different kind of support reaction. So I would recommend all of you to print this, make a copy of it, and every time you do some tutorial or exercise which require you to define what is the reaction force acting on that particular support, you print this out and just refer to the image shown. Okay, so kalau roller, lain support dia. Kalau it's a fixed joint, lain support dia. If it's a rocker or a smooth profile, lain. So you just refer from this table. Okay. So let's look at some few practical example. Okay, in this figure, you have to first identify what type of support or joint this is. So you know there's a cable over there. It is connected by a pin. So the type of connection exists in this particular joint is a cable type. So if you refer from the table that I gave you previously, then the support reaction would only be one tension force acting along the direction of the cable, and that is an angle theta measured from the x-axis. So accordingly, our corresponding support reaction would look something like this. Okay, there's a tension force at the cable and theta is measured from the x-axis. Sama je kan? Okay, now let's look at the second figure. Okay, first, what type of joint is this? So this is a type of pin. Okay, the connection is pin, and if you refer from the table on the item number 8, smooth pin or hinge, this is the type of corresponding reaction which will happen at a pin joint. So there will be one force on the x direction and one force in the y direction. So accordingly, if we redraw the support reaction in our picture, this is how it looks like. Okay, so it's quite straightforward. Okay, the next one, what type of joint is this? So you can see there's like a kind of roller, kind of rocker. So you refer to that table and you can identify that this connection type is known as the rocker joint. Okay, so rocker joint, if you refer from the table again at item number 4, it will have one corresponding force which is perpendicular or 90 degree to the surface of the contact point with that particular beam. Okay, in this case, this is how the support reaction would look like in our picture. Okay, so notice that the direction is perpendicular or 90 degree to the surface, to the contact surface. Okay. Okay, let's look at this example. In solving many engineering mechanics kind of problem, usually it requires you to draw the free body diagram of the system. So in this case, the system given is a foot level. Okay, so also given in this question is that the operator applies a vertical force to the pedal. So that spring ni stretch 40 mm and force at the short link is 100 newtons. So this is already given. Now let's translate all that information into our picture here. So you know the operator ni lah kaki dia kan. So it apply a vertical force. Kalau vertical force, this is how the direction of the force would look like, and let's call this F. Okay, so kita tahu the spring is stretched 40 mm. So this is the spring. Kalau dia stretch, then the direction of force would be over here. So kita tak tahu what is the magnitude of the force yet, but we know that the elongation of the spring, let's call it X, is equivalent to 40 mm. Okay, and then another information given in the question is that force at the short link at B, okay, so this is the short link at B, is 100 newtons. So there is also another additional vertical force acting at this particular link in the magnitude of 100 newton. So let's call this FB. Okay, so generally this is how the free body diagram looks like. But if you notice, it's not mentioned in the question, but there is another joint at A. Okay, kalau you tengok joint dekat A ni, it is like a pin joint. So if you refer to the table given to you earlier, kalau pin joint ni, dia akan ada dua reaction force, which is in the y direction. Let's call it FA Y, and also in the x direction, and let's call it FAX. Okay, now if we want to redraw this system into a free body diagram, remember free body diagram, you have to free up one component. You don't have to redraw everything including kaki operator too. No, you just focus on the item that you want to study. So in this case, the item that we are interested in is this particular triangular beam. Okay, and this beam is being subjected to a vertical force by the operator, which is in the magnitude. Magnitude is not given, so you can just represent the force like this. Okay, and then you know that there is point A over here, and at point A there are two forces acting on it, which is the support reaction force in the y direction, and I'll call it FAY, and also the support reaction force in the x direction, and I'll call it FAX. Okay, at this point mungkin you keliru, nak ke kiri ke kanan, it doesn't matter. This is just initial assumption sahaja. So kalau you perform the calculation and the equilibrium condition, then only you know if your calculation is correct or not. Okay, ada lagi tak force in this system? Ada, from the spring. So you know there's a force from the spring over here, and let's just call it Fs, which is a force caused by the spring. And given, maybe you can put some information here, given that the elongation of this particular spring is 40 mm. Okay, you can put all the information like this. And ada lagi tak force? Ada. There's a force at point B caused by the link. So the force is also horizontal direction. So given the magnitude of FB is 100 Newton. Okay, is there any more additional force acting on this particular triangular beam? Tak ada. There is only let's see, 1, 2, 3, 4, 5 forces acting on it. Along the x direction, there is 1, 2, 3 forces acting on the x direction, whereas along the y direction there is 1, 2 forces acting on it. So accordingly, when you have draw the free body diagram, then only you can perform the equilibrium condition. Calculate the corresponding forces in x direction or in y direction, and then you equate all the magnitude into 0 or kosong. Okay, so this is how you construct or draw the free body diagram. Okay, now let's look at this example. In this example, given a beam which have different kind of support at point A and also point B. Okay, so they wanted to know what is the reaction force at point A and point B basically. So given in this question is that point B is a pin. Usually they will give you a statement in the question to give you an idea what is the type of connection at that particular point. Okay, so in this case, dia bagi tahu at point B it's a pin. So if you refer to the support reaction table which have been provided in your lecture notes, if the support is a pin type, then there are two forces acting on that particular point, which is one force is in the y direction, and let's call this FBY, and there's also another force in the x direction, so let's call this FBX. Okay, kiri kanan atas bawah tu it doesn't matter, yang penting sekarang you just draw the free body diagram dulu. Okay, the next information given in the question is there is a rocker at A, so the type of connection at A is rocker, and again if you refer to the support reaction table, there is only one vertical force acting which is perpendicular to the surface, to the contact surface. So we are going to call this FAY. So ada apa-apa lagi yang aneh tak dalam this free body diagram? Okay, if you notice the 600 Newton ni arah dia sengit-bengit macam ni kan. So as usual, in order to ease your calculation, you can resolve this 600 Newton into the vertical and horizontal direction. So if I were to resolve it into the X or the horizontal direction, this is the direction of my force and the magnitude would be 600 cos 45. Okay, as simple as that. And if I were to resolve it in Y direction or in the vertical direction, so the magnitude of this particular force would be 600 sine 45 degree. Okay, now all is well, all is good. So the next thing we need to do is to apply the equilibrium condition for this free body diagram. So in equilibrium condition, we assume that all the forces is equivalent to 0. So now let's solve it one by one. So first we solve it in the X direction dulu. So assuming that rightward direction is positive, so we want to make sure that the summation of forces in X would be equivalent to 0. Okay, so dekat X direction there is one force over here, so I'll just rewrite it as 600 cos 45. It's positive because it's to the right, and then there's another force over here which is FBX, and FBX is directed to the left. So if it is directed to the left, then it will be minus FBX. Okay, so the initial assumption is the FBX is directed to the left. No problem, jangan risau. You just apply the equilibrium condition lah. So ada lagi tak any forces in the X direction? No more, there's only 2, so you can sum up this to 0. Okay, so this equation is quite straightforward. You can simply find your magnitude of FBX by rearranging the equation, and it will become 600 cos 45. So if you tekan your calculator, it will be 424.264. And the unit is in Newton. Okay, the magnitude is positive direction, so it means that the initial assumption is correct. So in this case, your direction of FBX is to the left. Okay, some of you may be triggered at this point. Kenapa to the left pula? Usually to the left kan negative value, ya? Okay, remember, your initial assumption of FBX is to the left. So, in the equilibrium equation that you construct, you apply negative FBX because you assume it to be to the left. So, when the final magnitude is positive, it means that your direction yang you assume tu betul because you already apply the negative FBX in the equilibrium equation dekat the second layer tu. Okay? Now let us apply the equilibrium condition in the Y direction pula. So in this case, assuming that the upward direction is positive and the summation of all the forces exist in Y direction is equivalent to 0, then kita total up all the Y forces, which is the first one is FAY. Okay, so FAY will be positive because it is upward. And then the 600 sine 45, it will be negative because it's pointed downward. And then what else? Oh, this 100 Newton, don't forget. So it's negative because it's pointed downward. And then the FBY is positive because we assume it to be upward direction. And oh, there's another 200 Newton over here which is negative because it's pointed downward. Okay, so this summation of all these forces would be equivalent to 0. Okay, so now there are two unknowns, which is FAY and FBY. Sorry, I forgot to put a Y here. So let's just put all the unknown variables in the left side equation. So FAY plus FBY would be equivalent to 600 sine 45 plus 100 plus 200. So I'm just going to solve this using my calculator, and I will get a corresponding value of 724.2641. Okay, at this point there are two variables, there are two unknowns, which is the FAY and FBY. So we cannot solve this equation yet. We have to come up with another new equation. And in order to come up with another new equation, we have to consider the moment equation pula. Okay, so you can measure the moment either in the A point or at the point B. It's up to you. But I think for the purpose of convenience, I'm going to measure the moment at point B because I can cancel out many forces. Okay, so if you want to apply the equilibrium condition for moment, so we assume counterclockwise direction as positive and summation of all the moment at point B is equivalent to 0. Okay, so it's not necessary lah you apply kat B. You can also apply the moment at point A. It's up to you really. So I apply it at B because there are many forces over here that I can cancel out actually. Okay, so now let's recall the moment equation. Moment is equivalent to F multiplied with the perpendicular distance, M equals to FD. So moment is caused by force multiplied with the perpendicular distance. So what are the force exist over here? Okay, let's look at the first one. So there's FAY over here. Okay, and then the distance, the perpendicular distance to point B is 2 meter plus 3 meter plus 2 meter. It will sum up to 7 meter. Okay, so I'll just multiply with 7. So what is the direction of this particular moment? If you draw an imaginary circle around point B, you will generate a clockwise kind of direction. So because it is clockwise, then it will be negative. Okay, now this is done. How about this 600 cos 45? Okay, if you look carefully, this 600 cos 45 is acting on top of the surface of the beam. Dia bukan melalui point B. It's on top of the surface. Okay, so there is a moment acting caused by this 600 cos 45. So if I rewrite the force of 600 cos 45 and the perpendicular distance to point B, kalau you tengok point B ni is in the middle of the beam. So if I project like dia punya middle point over here, so the perpendicular distance from 600 cos 45 to point B is actually 0.2 meter. Okay, so accordingly, if I were to create an imaginary circle around point B, then it would be in clockwise direction. So again, this would be negative. Okay, so now how about this one, 600 sin 45? Yes, there is a moment over here. So 600, and the distance is 3 plus 2 is 5 meter. So 600 sin 45 and the distance is 5 meter. How about the direction? If you draw an imaginary circle around point B, then the direction of this moment would be counterclockwise. So it would be positive. Okay, ada lagi tak force? Okay, how about this 100 Newton. So 100 Newton, the perpendicular distance to point B is 2 meters. So 100 multiplied with 2. So 100 multiplied with 2 and draw the imaginary circle around point B. It will be counterclockwise juga. So counterclockwise will be positive. Okay, ada lagi tak? Okay, now if you look at this 200 Newton, 200 Newton actually passes through the rotation point B. Okay, if the force passes through rotation point, meaning the distance is 0. So there are no moment produced by this 200 Newton. Sama juga dengan FBY ni. The line of action passes through point B. So there are no force acting caused by FBY. Okay, how about FBX? Okay, notice the pin at B is acting to the middle point of the beam at point B. Dia bukan macam case yang 600 Newton ni. 600 Newton ni dia acting dekat atas beam. Kalau this pin at B, dia akan act exactly in the middle because it's attached to the middle of the beam. Okay, so accordingly, because this line of force passes through the rotation point, so our moment over here would be equivalent to 0. So there are no other force which result to moment. So all this moment that we calculated earlier would sum up to 0. So how many variables are there? Only one variable. So saya boleh just rearrange this equation. Let's say 7FAY would be equivalent to, saya bawa dia ke kanan, and then this one would be negative 600 cos 45 times 0.2 semua ni. I'm going to solve this using calculator terus. And you will get a corresponding value of 2236.4675. Okay, so now I can conveniently calculate my force at the y direction. 2236 ni divide with 7, I will get a corresponding value of 319.4954. And the unit is in Newton. Okay, so what is the direction? So sekarang ni the magnitude that you get is positive. It means that your initial assumption of the upward direction too is correct. So in this case, the direction of Fy is upward. Okay, so now if you apply the magnitude of Fay into equation 1, so let's call this equation 1. Kita guna persamaan serentak as usual. Substitute Fay into equation 1 Fby, whereby it will be equivalent to 724.2641 minus with the Fay, which is 319.4954, and you will get a corresponding value of 404.7687. Unit is Newton. So apa maksudnya? If it is positive, meaning your initial assumption which is upward direction is correct. So the direction of this magnitude is upward. So that is how you solve the equilibrium condition for a rigid body. Tada, dah siap. Senang je kan?